Good morning again. On this day, April 29th, 2021, Thursday, last video was interrupted, so I had to do it again. To continue that one, that talk, I continue. Sorry for that. Its title is same: Civil Field Engineering, Designs, Construction Methods, Contracts, AnnexSL, Organizations, Communications, Coordination, Quantity, Quality, etc. etc. And this is revision A. Because of that, I was talking about quality and related COVID issues, as well as I was talking about pulverized coal, which this graph that was temperature versus pressure, and it is pulverized coal, an overview, pressure and temperature, water equilibrium diagram, in which I said temperature remains below freezing to 374, and here is pressure 22 when 374 temperature, and this is saturated vapor pressure curve. It says temperature rise up to 374 and pressure rise up to 22 from 6.1 to 25 more, and then if it crosses that one, you will find up to 0 degrees Celsius and between pressure 22 to 30 MPa. It is solid ice you can say. And when you go to temperature 0, freezing temperature to 374, means raise up temperature. 374 is too high, 100 is here boiling temperature, and then 374 and pressure from 22 MPa to 30. It's liquid water. Of course it's hot, and says subcritical water here in this range. You can say this elliptical curve here, parabolic elliptical, says this is subcritical water. And if temperature range of 374 onwards to 600, you can say here temperature up to 22, this is gas or steam. Steam which lies within range of 374 degrees to 600 degrees. It's too high because even boiling temperature is 100, and you can say steam is start building in, but 374 is very high. Steam range from 374 to 800, 600. Gas, steam it is, and up to pressure 22 MPa. Then if you go in same temperature range from 22 to 30 MPa, it is supercritical water. So this is subcritical water with below 374 degrees Celsius and between 374 degrees to 600 degrees Celsius, supercritical water between pressure 22 MPa to 30 MPa. And this is gas. Then you go further and see what happens there. Hourts is not shown this. It's called advanced ultra supercritical water. In this stage, ultra advanced ultra supercritical water in this stage here, and this is ultra supercritical water, and temperature rises there, pressure rises. This is what says. Then if you go further onto this, now it says supercritical power plants. Supercritical power plants were in service in late 1950s, but technology did not really take off due to problems of reliability, especially from metallurgical aspects. And so Denmark was first in Europe to build ultra supercritical plants, but Germany followed very soon after, later on also Italy. Ultra supercritical plants with steam temperatures around 600 Celsius is now considered state of art in Europe, Japan and China, whereas United States has still not implemented this concept. It was development of steel grade 91 and later 92 for heavy section, tubular components and derivatives for the cast and forged components that made this possible. Main advantage between subcritical, supercritical and ultra supercritical units and reason for higher pressure operation is increase in thermodynamic efficiency of Rankine cycle. From subcritical to current state of art of ultra supercritical, efficiency increases is about 7%, targeting about 16% with most optimistic ultra supercritical project. Now it's that a curve increase of net efficiency from subcritical to ultra supercritical power plant, and it is, you can say, subcritical cycle here 170 bar 540 degrees, then it is supercritical cycle 565 degrees 240 bars, it is ultra supercritical cycle here 250 bars 292 bars 610 6721, then advanced ultra supercritical from 345 bars onwards, and this is 650 700 and 760 degrees Celsius, and this is baseline, a change in overall plant net efficiency. And this is conventional steel, and this is nickel based alloys, this is state of art, and there's a lining here. You see baseline is here 0.0%, then it goes to 2.9% in this range, 5.8% in 250 bar range, 610 temperature rises, percentage efficiency is also here. So like this here is critical line 6.6%, in 292 bar 621 degrees Celsius it's 9.5 here, then it goes like 16%, 15.8 nickel based alloy. So this 6.6% basis percent to 15.8% nickel based alloys, and this conventional steel. So nickel adds to that, you can say. In this case, then we go to single most important factor, single most important factor that determines use of higher and higher pressure and temperatures is availability of materials to withstand these conditions. Increases in operating pressure, increases in operating pressure and temperatures have to go hand in hand with development in metallurgy. Last steel-based USC power plant is targeting a steam temperature in range of 650 degrees Celsius. For USC, use of nickel-based alloys is mandatory. Say last steel-based USC power plant is targeting a steam temperature in range of 650 degrees Celsius. For ultra supercritical, you can say, use of nickel-based. This is that one. Here I show you. Supercritical here. This is 650. Like that. Here in this range, it says that. Yeah. Last steel-based ultra supercritical power plant targeting steam temperature of 650 degrees. Use of nickel-based alloy is mandatory to reach a steam temperature over 700 degrees Celsius. Both for creep and corrosion, oxidation properties. Now this figure summarizes operating temperature and pressure of different available material classes. Schematic view of modified boiler for an USC power plant project proposed by Babcock and Wilcox, and here it is. Pressure, if you say 3000 onwards to 6000, and here is maximum mid-wall temperature, and that's up to 1600 degrees from 1000 onwards, and here it is today's technology limited by steel, it is here, and then it is USC technology requires nickel based alloys, and that is in this range. Pressure is 1400, and from here you can say it is 617, here in 740, and here like this is pressure, maximum operating temperature and pressure of different materials. This is that. So various materials are here, you can see, and this is just for information here. Then we go to this diagram, which is conceptual design of 800 megawatt modified tower for an advanced ultra supercritical power plant. This is 800 megawatt modified tower for an advanced ultra supercritical power plant. Here it is. And so this is regarding how it works. Our then shows how ratio between ferritic, austenitic and nickel based materials, ferritic, austenitic and nickel based materials for boiler components changing when going from supercritical to advanced ultra supercritical power plants. Now you can say 250 bar, 540, 552 ferritic. This is 280 bar, 80% ferritic. This is 56 ferritic and this is 31 ferritic. These are various stages. Other chapters of this book will give detailed information about material currently. Our issue was pulverized coal fired boilers. Pulverized coal, which is our topic here. Pulverized coal firing ensures complete combustion of coal. Complete combustion of coal, thus ensuring higher efficiency of steam generators. It's predominantly adopted in large coal-fired utility boilers. Finer grinding of coal, more efficient its combustion. Total time required from entry of a coal particle. See, finer grinding of coal means finer grinding, more efficiency in its combustion. Total time required from entry of coal particle to a furnace to combustion of particle is very short. This time, however, is dependent on various factors. Heat, see, heart of pulverized coal fire boiler is pulverizer. Heart of pulverized coal fire boiler is pulverizer, also known as mill. Pulverizer is known as mill. Depending on speed, pulverizers are classified as low speed, medium speed and high speed mills. Pulverized coal burners may be located on front or opposed walls or in corners of furnace. There are two types of fuel firing systems, bin system and direct firing system. Coal feeders are either volumetric or gravimetric type. Combustion and thermochemistry. Devolatilization of solid fuel. This by Shenling, Chang, Chen, Changsa. Devolatilization of solid fuel. Pulverized coal is used in many utility boilers. Due to small particle size, pulverized coal can be transported pneumatically. Coal particles contain four major components. Pulverized coal is used in many utility boilers due to small particle size. Pulverized coal can be transported pneumatically. Coal particles contain four major components: moisture, volatiles, char and ash. Moisture, volatiles, char and ash. When heated, moisture is dried out and volatiles are devolatilized. What happens when heated? Moisture is dried and volatiles are devolatilized. Volatile vapor mixes with oxygen and mixture burns. Volatile vapor mixes with oxygen and mixture burns. Char left on particles is burned with oxygen when contacted. Drying and devolatilization processes are controlled by heat transfer from gas to particles. Similar to liquid vaporization, heat transfer is convective. Empirical correlations are used to determine interfacial heat transfer rate. Similar Lagrangian and Eulerian approaches can be applied for particles. So let's go further. Injectants. Pulverized coal. Now, pulverized coal can be used as a reducing agent by injecting it through tirers. Coke has been replaced up to 250 kg with pulverized coal. Coke, no. Coals for PCI are usually cheaper, non-coking thermal coals. Important properties of coals are content of volatiles and moisture, chemical composition, sp alkalis ash, then grindability, hard grindability index, stability of quality. Coal is dried and ground to less than 0.1 mm grain size. 0.1 mm, 1/10 of mm. Pulverized coal is carried pneumatically to a bin and further to weighing and distributing system to be injected in blast furnace. Let us see this. Illustration of pulverized coal injection, PCI, pulverized coal injection in blast furnace. Hot gas generator, and here from what waste gas, ambient air, all this coming here, and this is, you can say, go to gas and air, hot gas generator, then goes to grinding mill, and then it is raw coal basin from coal field, and here pulverized coal, it is goes to bag filter from your fuel gas, and this is your fine coal silo. It comes here, transport nitrogen, and this is fine coal silo, bag filter, and here it is what you call iteration and pressurization. Illustration of pulverized coal injection in blast furnace. Blast furnaces here. Okay. Plastic, fluff, and other solids. Waste materials, plastics, and fluff can be recycled. Waste materials, plastics, and fluff can be recycled by injecting in blast furnace. Waste material like plastics and fluff can be recycled by injecting in blast furnace if they are ground to suitable grain size to be transported pneumatically, and if they contain enough of carbon that can be oxidized. These materials must not contain too much undesirable impurities such as Cl, Zn, P, Ls, etc. Blast furnace dust can be recycled by injecting it if its Z content is not too high to accumulate in process. Oil and tar. Oil and tar. Injection of oil was widely used before oil crisis in 1970. Since then, pulverized coal injection has been dominant. Equipment for oil injection is quite simple. Oil has been injected up to 150 kg per THM. Replacement ratio decreases from about 1.3 kg coke per 1 kg oil with small oil rate down to 1 kg coke per 1 kg oil with large oil rates. Light oil fractions are easier to inject and they have a better replacement ratio. Heaviest fractions, bottom oil, must be preheated up to 220 degrees Celsius before pumping and injection. Main disadvantages of oil are high sulfur content, strong soot formation with high injection rate and price. A typical composition of heavy bottom oil is C is equal to 86.6%, H is equal to 10%, S is 1.8%, N is 0.8%, and O is 0.8%. Surplus tar from coke plant can also be injected like oil in blast furnace. Tar is more abrasive for pumps than oil, and composition is given here, so it's just going to read that, no problem. Natural gas is widely used where available at reasonable price. It consists mainly of methane. Natural gas consists of methane, over 80% in volume, with a few percentage of ethane. Ethane and other alkanes. Main impurity is nitrogen, and rest is a small amount of carbon dioxide. Constituents of natural gas. Constituents natural gas of different countries. Say volume: Russia, Uruguay, Germany, USA, Holland, Norway. methane 98% to 93%. So in various ratios, in various countries, ethane. So main is methane, is natural ethane, propane, butane, nitrogen, carbon dioxide. These are natural gases, you can say, says natural gases from different countries. And methane from Russia, from Germany, from USA, from Holland, from Norway, like this. Also ethane percent is very low, not that much. Propane and butane, then nitrogen and carbon dioxide. Now natural gas is easy to inject and it is clean. Practically without sulfur, it has a strong reducing effect on adiabatic flame temperature. Lowest limit is claimed to be 2073 Kelvin or 1800 Celsius. The price of natural gas is really high. Low surface content brings several benefits. Better working conditions in cast house, higher carbon contents in hot meal, less need for desulfication. Higher H2 content top gas enables more electric power generation. Natural gas injection can decrease carbon dioxide emission depending on replacement ratio and injection rate. Coke oven gas. Coke oven gas COG is a strong fuel but less useful compared to other injected fuels in lower part of blast furnace. Coke oven gas contains hydrogen H2 60%, CH4 24%, carbon monoxide 6%, carbon dioxide 2%, nitrogen 6%. Only carbon CH4 is oxidized in raceway to carbon monoxide, releasing heat. CO2 reacts with coke carbon to CO, consuming energy, whereas H2, N2 and CO are only heated up in the raceway. Advantage of H2CO is reducing gases. Comes in use in upper part of furnace. COG lowers adiabatic flame temperature more than other injected material. Electric power generation fossil fuel. Pulverized coal combustion in superficial steam cycle. Pulverized coal combustion in supercritical steam cycle. Pulverized coal fired supercritical steam boilers have been in use since 1930, but improvement in materials and increasing demands for higher efficiency are making this system choice of new coal-fired utility plants worldwide. Increased efficiency is due to higher mean temperature of heat addition in supercritical steam cycle because of strong increase in moisture content of high pressure steam as it expands through last stages of steam turbine. Steam has to be reheated by taking it back from turbine to boiler. Reheating once or multiple times will raise also thermodynamic efficiency, that is reheating once or multiple times will also raise thermodynamic efficiency of power cycle because it further increases mean temperature of heat addition. Advanced supercritical steam power plants with steam parameter of 300 atm pressure, temperatures of 866,000 and cycle efficiency up to 43% are expected to play a major role in new power generation in near future. As steam temperature approaches 973 Kelvin, the efficiency may reach 47%, but new advanced designs and materials for boiler, steam turbine and associated piping will be required. Development like yield commercial application now. Coal used in iron and steel manufacturing, steel metallurgy, blast furnace iron making, carbon used in blast furnace in form of both coke and auxiliary reducing agent is discussed now. Coke use and quality. Coke is virtually universal with energy source. Coke fulfills three primary functions, that is, it supplies heat, it acts as a reducing agent, it supports burden. Coke is carbonizing agent and dust filler. Carbon of coke and of auxiliary reducing agent supplies major part, approximately 80% of heat required for process. Heat required for endothermic extractions, preheating and melting charges. So carbon and oxygen react to carbon monoxide. carbon and oxygen react to carbon monoxide either directly 2C plus O2 2CO or at high temperature 900 to 1000 degrees Celsius by means of bound round reaction. So that's our theory here. Coke also was, so we want to see, yes, this is what it says. Carbonization is there, top gas temperature, alright, that's fine. What we are interested in. Quality records of coke, fine, chemical properties are here. And then what we are searching for is coke degradation, alright, it's all that. For our purposes, other one. This is reducing agent consumption of German blast furnace, and this is you can say year-wise. Okay, then we can go on further, and it is very much technical for you, so no need of wasting time here. I'm interested in pulverization, that's very important, and this is conversion degree. Types of firing systems. This is here cyclone burner at Paradise fossil plant. Okay. Well, I think there's not much available for this stock. Let us see what says. Pulverized coal. This I think last page maybe. Pulverized coal consists mostly of particles capable of passing through 200 mesh screen. So pulverized coal consists mostly of particles capable of passing through 200 mesh screen, which corresponds to diameter 74 microns and lower. For coals of high volatility and low ash content, combustion of characteristics are comparable to those of liquid fuel sprays discussed on. With decreasing volatility and increasing ash content, lower limit of inflammability shifts towards fuel rich site, indicating effective radius of particle for flame transmission decreases. Particles of anthracite or coke containing little or no volatile matter do not transmit flame at ordinary ambient temperatures because they lose heat by radiation more rapidly than can be supplied by oxygen molecules that impinge and react on their surfaces, and thus do not maintain high temperatures necessary for rapid reaction. In order to burn pulverized and thrust coke, it's necessary to surround flame with reddish. All right, now I think this is over, I can say. So we have gone through this talk of. We're going to find more material after that, so better I close this for current, and we go back to I think that file, which is where is that? And project designs, general facilities. I think this is engineering facilities, petrochemicals. This is GGBS. That was I talking about. We're talking about this. We are here. We've gone like this. We are talking about this is GGBS or we're talking about something here. Fly ash, yes, this is what we're talking about fly ash yesterday, and this was again I read fly ash is finely divided. We are talking about cementing materials, supplementary cementing materials we are talking about, just for your refreshing information. We are talking about supplementary cementing materials, and this is one of those supplementary cementing materials, and this is one of those PFA, pulverized fuel ash. Fly ash is finely divided, FINALY. Fly ash is finely divided residue resulting from combustion of pulverized coal that is carried from combustion chamber of a furnace by exhaust gases. Pulverized coal that is carried from combustion chamber of a furnace by exhaust gases. For reference, specification of use of fly ash in concrete are given, whatever specification, leave it behind. Fly ash is FCI or CH by its calcium oxide contents. So classification of fly ash is done as FCI or CH by its calcium oxide content. Type F refers to fly ash with calcium oxide content less than 8%. Calcium oxide content less than 8%. Type CI has a calcium oxide content ranging from 8 to 20%, and type CH fly ash has a calcium oxide content greater than 20%. Higher calcium oxide content generally denotes higher self-cementing properties. So 8%, 8 to 20%, and above 20%. Less than 8% is fly ash with calcium oxide. Type CI is 8 to 20% calcium oxide, and more than 20% calcium oxide as type CH. Then chemical composition requirements. Now, standard CSA A3003 standard permits maximum of 5% SO3 content for type F fly ash and a maximum loss on ignition LOI of 8%. Maximum loss of ignition 8%. Maximum SO3 and LOI contents for both types CI and CH is 5% and 6% respectively. SO3 content has been reported to influence to some degree early age compressive strength of mortar and concrete specimens. So SO3 content is reported to influence some degree early age compressive strength of mortar and concrete specimen. Higher SO3 content, higher is resultant early strength, age strength. However, maximum limit on SO3 is considered necessary in order to avoid an excess sulfate content in hardened concrete, which may contribute to disruptive expansion due to internal sulfate attacks. So sulfate is a question mark here. Concrete must have a boundary that much content of sulfur is acceptable. Loss on ignition LOI is determined by mass loss of fly ashes heated at a temperature of 750 plus minus 25. This means 725 to 775. Unburned carbon is largest component of LOI. Unburned carbon. Water required for workability of concrete is influenced by carbon content. Water required for workability of concrete is influenced by carbon content of fly ashes, while shape of carbon particles, that's called porosity. Higher carbon content of a fly ash, more water is needed, produce a paste of normal consistency. Also, doses of air entraining admixtures for fly ash concrete to achieve a certain air content increases with an increasing carbon content in fly ash used. Carbon absorbs organic admixture such as air entraining agents. Water demand and doses of air entraining admixtures both increase with increasing porosity of carbon particles. Physical properties and requirements. Physical properties of fly ash may vary over a wide range. Specific gravity, for instance, ranges from a low value of 1.9 in some fly ashes to a high value of 3 for iron-rich fly ash. SG value, specific gravity value of around 2.2 being however common. By comparison, specific gravity of Portland cement is 3.15. Specific gravity is 3.15 Portland cement. Fineness is one of primary physical characteristics of fly ash that relates to its pozzolanic activity. It's well known that particles larger than 45 microns show little or no reactivity under normal hydration conditions. It's been reported that pozzolanic activity is directly proportional to amount of particles finer than 10 microns fineness. You can say pozzolanic activity depends on finer than 10 microns fineness of fly ash ranges from less than 2% retained to more than 30% retained on 45 micro MCU. Mineralogical composition. Here is mineralogical analysis of fly ashes typically shows 50 to 90% of non-crystalline particles or glass and some crystalline phases. 50 to 90% of non-crystallized particles or glass and some crystalline phases, that is of fly ash, shows 50 to 90% non-crystalline particles. Reactivity of fly ash is predominantly related to non-crystalline phase of glass. Higher calcium fly ashes, namely CH, contains significant quantities of reactive crystalline phases that influence properties of fly ash in concrete. Quality control. Fly ash from a given power plant may vary with time depending on many factors such as changes in burning conditions or source and composition of coal. Variations in fly ash properties may affect performance of concrete. Fly ash properties that are most likely to affect its performance in concrete are fineness, particle shape, glass content, and composition. Loss on ignition, autoclave expansion, SO3, CO, and alkali content. Variability of fly ash color should also be monitored for architectural concrete applications. Changes in fly ash color can also indicate changes in carbon content or power plant burning conditions, which may affect performance of fly ash in air-entrained concrete. Ground granulated blast furnace slag, GGBFS. Ground granulated blast furnace slag, very important material, very important material from every viewpoint. I think its most reliable one, GGBS, ground granulated blast furnace slag, is a non-metallic product consisting essentially of silicates and aluminosilicates of calcium. Silicates and aluminosilicates of calcium and other bases. Developed in a molten condition simultaneously with iron in a blast furnace, followed by water chilling rapidly to form glassy granular particles, and then ground to cement fineness or finer. Again, it's very important sentence. Ground granulated blast furnace slag is a non-metallic product consisting essentially of silicates and aluminosilicates of calcium and other bases, developed in a molten condition simultaneously with iron in a blast furnace, followed by water chilling rapidly to form glassy granular particles, and then ground to cement fineness or further finer. In concrete, GGBS reacts with Portland cement to form cementitious products. Slag possesses both cementing and pozzolanic properties. Cementing and pozzolanic properties noted. Chemical composition requirements. Compared to fly ash, GGBS is usually rich in calcium and magnesium oxides. Rich in calcium and magnesium oxides. For similar reasons as mentioned above for fly ash, CSA 3000 limits SO3 and sulfur and sulfide sulfur contents in GGBS to 4 and 2.5% respectively. So SO3 and sulfide sulfur contents 4 and 2.5 respectively. Physical properties and requirements. Unlike fly ash, GGBS is ground to desired particle size or surface area depending on degree of activation required as well as economic considerations. Reported that slag particle less than 10 micron contribute to early strength developed up to 28 days. Slag particles less than 10 micron. Particles in 10 to 40 microns, 10 to 45 microns range continue to hydrate beyond 28 days and contribute to later age strength, while particles above 45 microns generally show little or no activity, typically in order to obtain satisfactory strength. Development in concrete. Plane surface area of GGBS ranges between 4,000 to 6,000 centimeters square per gram. 4,000 to 6,000 centimeters square per gram. In order to avoid disruptive expansion of concrete containing GGBS due to MgO content, expansion to 0.8%. Again I read this physical property. Unlike fly ash, GGBS is ground to desired particle size or surface area depending on degree of activation required as well as economic consideration. Reported as slag particles less than 10 micrometer contribute to early strength development up to 28 days, and particles in about 10 to 45 micrometer range continue to hydrate beyond 28 days and contribute to later generally show little or no activity, typically in order to obtain satisfactory strength development in concrete. Plane surface area GGBS ranges between 4,000 and 600 centimeters square per gram. This means 4,000, which is, if you take case of, let us say 400, let us say 200 by 200, 20 by 20, you can say 200 by 20, 200 centimeter by 20 centimeter. We take 200 centimeter by 20. If you put 1 gram cement spread on this area, that's called plane surface. Now, mineralogical composition. Mineralogical analysis of GGBS samples show glass content ranging between 80 to 100%. Glass content. Mineralogical analysis of GGBS samples show the glass contents ranging from 80 to 100%. As a fly ash, reactivity of GGBS is strongly dependent on glass content. Reactivity of GGBS is strongly dependent on glass content. Now, blended hydraulic cement. Blended hydraulic cements can include various proportions of 1 binary, 2 ternary, or 3 quaternary, SCMs such as fly ash, GGBS, and silica fumes. So it says blended hydraulic cements can include various proportions of binary, that's 1, 2, ternary, 3, quaternary, supplementing cement materials such as fly ash, CUS, and silica fumes. These cements can be used with additional fly ash and slag added at concrete batching plant. Aggregates. There are many reports indicating that alkali aggregate reactions can be mitigated by proper use of fly ash or GGBS. Proper amount of these SCMs to control alkali aggregate reactions in concrete shall depend on reactivity of aggregate and should be determined through a testing program. Chemical admixture. Chemical admixtures used in concrete incorporating SCMs should conform to codal requirement. Just give me a few minutes because it's also important to go for a couple of. I'll be back. I'll be back. What's that? Oh, I didn't hear that. I was. I said that. I forgot that. I think. Yeah. I forgot that. Was it? So here back I can say now we can say that there are many reports indicating the alkali aggregate reactions can be mitigated by proper use of fly ash or GGBS. So for neutralizing alkali aggregate, GGBS or fly ash are solutions. Proper amount of these SCMs to control alkali aggregate reactions in concrete shall depend on reactivity of aggregate and should be determined through a testing program. Chemical admixture used in concrete loss on ignition value of fly ash. It also